Today discuss about field control DC motor. First of all, this is an equivalent circuit diagram of field control DC motors. And first of all, the transfer function of a field control DC motor relating angular shift in the shaft and the input field voltage VF. This input field voltage VF is derived in this picture. The circuit diagram is shown in this picture, where the VF is equals to input voltage to the field winding, which has a resistance and an inductance RF and LF respectively. This is RF and LF respectively. The armature current IA equals to supplied to the armature is kept constant, and thus the motor shaft is controlled by the input voltage VF. The input field current IF, so here input field current IF produced a flux in the machine, which in turn produce a torque at a motor shaft. The moment of inertia and the coefficient of viscous coefficient of at the motor shaft are Jm and Fm respectively. Please note down the angular shift resulting in the motor shaft being theta m. This is a theta m, and the corresponding angular velocity equals to omega m. Okay, this parameter is very important. Since the armature current is kept constant, so therefore we write that our relationship, that's the motor torque Tm replaced by Tm, which is proportional to the IF field current, and this equals to basically the constant Kf into IF. So Kf equal to motor torque constant. Okay, and now if we apply the KVL equation at this input, so we see that Vf equals to IFRF, okay, plus LF dIF by dt. So this is our KVL equation at the input side. This is IF, this is input side, and we also know that Tm equals to Kf into IF. Okay, so now what is another expression of Tm? We already know that for the rotational system, these are from the above equation. So this is our expression. Okay, so now we put here, but one thing should remember here, J equals to Jm and d2 theta by d theta m by dt2 plus Fm and d theta by theta m by dt, d theta m by dt. Okay, so now express this equation in the form of angular velocity. We know that omega equals to d theta by dt, angular velocity equals to theta d theta by dt. So therefore Tm equals to, again express this equation, Jm into d omega m by dt plus Fm into omega m. So these are final equation. Now we take the Laplace equivalent equation of this. So now this equation is in Laplace form is VFS plus RF into IFS plus LF into IFS. IFS. This is the first Laplace equation. Next, TMS. This equation, TMS equals to Kf into IFS. Now for the third equation, TMS is equals to Hs square, because second order derivative, the Laplace transform is theta ms plus S of Fm theta ms, and the last equation, TMS equals to S into Jm into omega ms plus Fm into omega ms. So these are Laplace equivalent network. Okay, so now for the equation, if we now from this equation, we see that IFS here is basically equals to VFS divided by RF plus LF. Okay, so now if we consider one block here, so now if we consider, just a minute, now if we consider here one block in a block representation, so now here first of all this is a VFS, the input side, the input voltage, and in this block contained 1 by RF plus S into LF, and the output equals to gives the field current IF expression Okay, that is equal to IFS, sorry. And next, to produce this TMS expression, so now this is another block coming out, that is KF, and the output equals to TMS. Okay, TMS. And now the second transfer function between the TMS and the theta. So now here one block is present, and at the output of this block, this is a theta s. So what is the relationship between theta and t? If we take the transfer function, then theta ms by tms equal to s squared jm plus sfm. Okay, now here we write jm s square plus fm into s. So this is a transfer function. So now this is equivalent block diagram. Okay, these are very important. So now this is a block diagram, this is a final output theta, and this is input voltage. So you see that this is a block diagram of a field control DC motor relating to the value of theta ms and the input field voltage vf. Okay, so now if we take reduction of this block diagram, so these are vfs, yeah, right, vfs, and apply the series rule from the block diagram in the previous video. You see that, so this is kf into divided by rf plus s lf in the bracket jm s square plus fm into s, so in this bracket. So now what are the output? The output equal to theta m into s. Okay, so this is the deduction method of the block diagram. So the overall transfer function equal to theta ms by vfs equal to this. So this is the overall transfer function. Okay, so that is very easy to derive it. And another equation there are related to between the omega m and vfs, which is also derived by this expression. So now if we relate the equation between omega and the value of field control voltage vfs, so now we see that vfs equal, we apply here, and here in this block 1 by rf plus slf, this basically produced, what is the value of produced, the if into, then if we multiply it by kf, and then here instead of the second order differential equation, if we take this expression, okay, this is the value of omega, so therefore here 1 by jm into s plus jm into s plus fm, okay, because this is a, sorry, this is a basically expression of omega ms, because here the transfer function omega ms by tms equals to s jm plus fm. Okay, clear? So what is the value of tms? So this is the value, basically value of the tms, because tms equals to this into kf. Okay, so from this equation, from this again this expression. Now this is a block diagram method to analyze the field control DC motor from its equivalent diagram. Okay, so now we discuss about one more thing, that is armature control DC motor. Okay, now first of all, the circuit diagram of armature control DC motor is given by, this is one resistance RF, and here one inductance is present LF, and here the constant current is flowing. This is a, here the potential equal to EB. Okay, sorry, just taken right here, this is EB EMF, and the rotation parameter constant is Jm and Fm, and here one resistance that is called RA, armature resistance, armature inductance, and this is an output, this is basically theta m, and this is a VA, sorry, this is the input side. Okay, and these are IF constant current, and here the current is IA, armature current. Okay, so now input voltage VA is applied to the armature. So now this is the input voltage is applied to the armature, which has a resistance RA and the inductance LA. The field current IF, this is IF, is supplied to the field winding kept constant, and thus the armature input voltage control the motor shaft output. And here the moment of inertia and the coefficient of viscous friction at the motor shaft being Jm and Fm. This is a viscous coefficient and these are basically moment of inertia. Okay, now as the field current kept constant, the relationship between the torque, and again we write here Tm is proportional to, yes, right, what is armature current, and for equal to of this equation is a kt some parameter are coming, is a known as motor constant parameter, motor constant. Now applied input voltage Va, this applied voltage input applied input voltage Va opposed by the back EMF Eb, this is a back EMF by this armature developed in the armature, and the relationship between Eb and the motor speed, and the speed of the motor is omega m. So now this is a Eb is proportional to basically omega m. Student, this parameter is very, very important. Please note down that is the back EMF is proportional to the motor speed omega m, and from this expression omega m equal to d theta m by dt, and therefore Eb equals to some constant kb d theta m by dt. This kb is known as back EMF constant. Back EMF constant expressed in volt per radian per second. Okay, now the related dynamical equations for this equation. Now for this equation right here, this is very important. Now this is they have back EMF generated Eb. So now if we apply basically KVL equation at the output, therefore Va minus Eb, because they are opposite phase, that is equals to 2 voltage developed Ia into Ra, because in this resistance and in this inductance the current equals to Ia, as you already told about that. This La equals to dia. Ia means armature current. Okay, dia. Okay, now again the another relationship is Eb equals to kb into d theta m. So basically for the different types of motor, different types of armature winding, the basic parameter are the very important to analyze the system transfer function kb into omega m, this relationship, and Tm equals to basically kt into Ia, and again from the inertia equation Tm equals to, we know that Jm into d2 theta by dt2 is basically theta m plus Fm d theta m by dt, and again Tm is equals to Jm d of omega m by dt plus Fm into omega m. Okay, so this is the expression. Now if we take the Laplacian equation, Laplace equivalent equation, so these are very easy. These are Vs minus, these are capital notation used for in a Laplace domain, Ra into Ias minus plus S into La into Ias. So taking all the Laplace equivalent equation, so this is a EBS is basically equals to KB is, because it is a first order derivative, this expression, and next EBS is basically equals to KB into omega ms. So now take this Laplace equivalent and so on. So now we see that these are very important tasks for us to analyze the block diagram of armature controlled DC motor, the relating parameter of theta and the VAS. So this is very important. So now see that from the equation, this is very important, and the equation, say for example, this is okay. First of all, we find out this expression, because this all expression is very important for to analyze the block diagram. So this is S square. Okay, students, please follow it properly, otherwise you cannot draw the block diagram properly. So this is Fm into S into theta ms. Okay, right? So this is a time domain approach, this is a Laplacian domain approach, and last equation is known as TMS, is also expressed by Jms into omega ms plus Fm into omega ms. Okay, now we see that from this equation to this equation, from this equation to this equation, and there's some relation have been coming out. And first of all here noted that First of all, from this equation we see that here VAS minus EBS is basically equals to RAIS. Okay, so that is here from here armature current parameter is constant, therefore this is RA plus LA into S. This is a parameter. Okay, now see, this is okay. Now okay, now here from the block diagram concept, if we apply here our input voltage VAS for the field controlled field controlled armature controlled DC motor, sorry, the input field is basically VAS. Okay, and now this is a one block is used here, and here the EBS is basically back EMF, and here the error signal is generated between the input and the back EMF. So now here one block diagram is present, which is 1 by RA plus LAS, because these are transfer function between these relationships. Okay, and the output equals to basically IAS. Now one parameter is coming out. Okay, now you see that from this IAS equation, now you see that this is very important. Okay, student, please note down, now from this equation IAS is IAS into KT into TMS. Okay, so now here one present block is known as KT, and the output is equals to TMS. Okay, so the arranging of equation is very important, and these are TMS and one block, the TMS relationship between the theta. So now this is a basically theta. Now students see that this is a basically theta ms, and what are the relationship between theta and t? This is the transfer function jms square plus, okay fine, 1 divided by jms square plus fm into s. Okay, inertia and the, yes, right, viscous coefficient of the system. Now one thing should be remembered, that these are theta ms, and now what is the expression between the EB and the theta? Now see that this is very interesting. Now this is a skb. S is a Laplacian coefficient, and kb is the, as you already told, that kb is a, what is a kb? Yes, right, very good, back EMF constant. Okay, the back EMF constant. So now relate between them. Yes, basically this is a feedback path gain. Now see that this is a closed loop control system. Okay, now for the armature control motor, there is a closed loop control system. There is error correction between the input and the back EMF, and produced, and some gain parameter are G1, G2, G3 produce the output, and then theta is also coming back this skb by this skb block. So this is basically the block diagram representation of, yes, armature control DC motor relating to the parameter theta and the VS. And you also it is your home task to draw the block diagram, BD means block diagram, between omega ms and the VAS. So basically this equation helps you 1 2 3 4 5, from this 5 equation you again plot the block diagram block diagram of armature control DC motor. Okay, so that's all for today. Thank you.